Okay, good morning. This is Mrs. Kern, and I'm going to show you today how to make soap. But first, we're going to do a little discussion of the chemistry of soap, a little bit of background before we start the lab. So, on the board behind me, I've got the reaction for making soap. This is a general reaction. We're going to use a lot of different oils to make our soap, and I'm showing you what one of the oils might look like when it reacts. So here we have glyceryl tristearate. We're going to react it with 3 molecules of sodium hydroxide for every molecule of that. And we're going to get a molecule of glycerol and 3 molecules of sodium stearate. And the sodium stearate is the soap. Glycerol is kind of a glycerin or glycerol. It's a thick viscous substance that's really moisturizing, so if you have it on your hands, it kind of feels nice. It's kind of sticky though, so you wouldn't want to have just that on your hands. Sodium hydroxide is a strong base, and glyceryl tristearate is, like I said, it's a component of the oils that we're going to use. So we're going to use a mixture of a bunch of different oils, but they're all going to behave in approximately the same way. So we're just using this as our general one. So this is the soap molecule that we're going to form, sodium stearate. Can you see the sodium ion down there? There you go. So you'll notice it's got a really long chain of carbon atoms, single bonded, and these little black lines are hydrogen atoms attached. And at the end of this long chain, you've got this portion, which has 2 oxygen atoms. And the whole thing has a negative charge. But because the oxygen atoms are so electronegative, those electrons are going to hang out mostly, they're going to be pulled somewhat toward this end. And so this end is going to be partially negative. And then it's attracted, of course, to the sodium ion, which has a +1 charge. So we'll be forming this ionic compound. So the sodium stearate that we're going to be forming here, we're going to get 3 molecules of it for every 1 fat molecule or oil molecule that we react with it. So we're going to get quite a bit. I wanted to show you how this is going to behave and why soap is so important. So we have this long end of the molecule that is just hydrogen and carbon atoms. And this thing is going to be what we call hydrophobic. Or it's afraid of water, right? So this is really an oil-soluble or fat-soluble portion of the molecule. Because it's fat-soluble, other things that are fat-soluble will be able to dissolve and be attracted to this end of the molecule. So things like oils that are on your hands, they'll stick to these soap molecules, this portion of the soap molecule. Dirt will do the same thing, it's hydrophobic as well. And things like the outer coat of a virus or the cell membrane for a bacteria. In both cases, soap molecules will stick to those, and sometimes they'll even break them apart and open them up. And in the case of a virus, we're doing these videos because we can't have school because of a viral outbreak. So in the case of a virus, when you open up that exterior coating, all that's left inside is the RNA. And RNA is pretty fragile, and it's not going to be stable in the environment. So it makes that virus no longer able to be spread. So we have the hydrophobic end of our soap molecule. Every soap molecule is going to attach to a bunch of different things that are on your hands as you're washing your hands. And then down here, this end is hydrophilic. Hydrophilic means water-loving. So this end of the molecule, well, first of all, you remember ionic compounds will dissociate in water, right? That means if there's a water molecule around, it's going to be oriented something like this, where its partial negative charge, it's a polar molecule, so its partial negative charge is going to be attracted to the sodium ion, and its partial positive charge on the hydrogens will be attracted to the negative portion of the stearate ion. So water is going to break up these molecules, but also water is going to be attracted to the stearate ion, well, to both of them. And as you have soap on your hands, and all these hydrophobic ends of the soap molecule are attaching to things that you don't want on your hands, like oils and dirts and bacteria and things like that, the water end, or the hydrophilic end, is going to be able to grab onto water molecules. So when you rinse, you're not just removing the soap from your hands, but you're removing everything else. The water's going to grab onto this end and just pull everything else off your hands, everything that's attached to the hydrophobic end. So that's a little background on how soap works, and we're going to have a little discussion about why it's really important to think of it as a reactant problem when you're making soap. Okay, so we're getting ready to make some soap, and I mentioned that soap making is definitely a limiting reactant kind of problem because the glyceryl tristearate that we're going to be working with that comes from fats or oils is not damaging to your skin. Actually, the oils I'm going to use are soybean oil, like cooking oil, vegetable oil that you probably have in your kitchen, and a couple of others. So if we had a soap product that had some leftover of this, the glyceryl tristearate, that would be totally fine, because if you have it on your hands, it's not going to hurt you at all. On the other hand, sodium hydroxide is a base, and it can be pretty damaging to your skin. At a minimum, it's going to make your skin dry and cracked and hurting a lot if you're using the soap a lot. So we want to make sure that every single molecule of our sodium hydroxide gets reacted and becomes soap, because this is not damaging to your skin. If we have a little bit of extra of this stuff, that's just fine. The only problem with this is that if you have too much extra of this, it is going to be a problem later on, because it will react with oxygen in the air, and we say that it goes rancid. Oils go rancid. They smell funny. The soap would still work. It would still be okay, but you wouldn't enjoy the smell of it, and it kind of leaves an odor on your hands, which is not a good thing. So we want to make sure we have close to the right amounts of each of these. Again, this is a 1 mole to 3 mole ratio, but we definitely want to make sure that this gets all used up. So here's a little practice problem. We'll try it and see what we think. We want to know which is the limiting reagent if we had these amounts of starting reactants. So limiting reactant means which of these two things limit how much product you can get. So we can pick either one that we want to work with, either of the two products that we want to work with, but we want to know which of these two is going to limit it. So if you ever have a limiting reagent question, or limiting reactant, same thing, if the question is what is the limiting reactant, the answer will be one of these two. So if you're doing some process of elimination, you can eliminate any products because they're not reactants, so they aren't the limiting reactant. So we're going to start with these two masses. So this is from the practice problem that I created. So let's say we have 100 grams of glyceryl tristearate and 53 grams of sodium hydroxide, and we want to know which one is going to limit how much product we use. Well, to solve this problem, we want to be able to compare the same two products based on these two reactants. So we could either do the glycerol or we could do the sodium stearate for our answer. And it doesn't matter as long as we match both of the answers so that they're really comparable. So I'm going to pick the sodium stearate. But again, you'd get the same answer if you use the glycerol. So we're going to go from grams of these things. The next step has to be moles, because these are not, because they have different masses, you can't compare them directly. So we're going to go from grams of glyceryl tristearate to moles of it. I'm abbreviating it. I should probably write out the formula, but it's kind of a big guy. And then we're going to go to moles of the product that we've chosen. Let's call this sodium stearate. Oh, gonna pause here. Okay, so we've got 100 grams of glyceryl tristearate, and we're going to go to moles of glyceryl tristearate, and then moles of sodium stearate, which I'm going to just abbreviate it like that instead of writing out the whole formula. And so we're going to convert, and we're going to stop at moles. We could go the next step and go to grams of sodium stearate if we wanted to. Either way, as long as we're consistent with our other reactant, we could find the right answer either way. So, got a 1 here. I already looked up the molar mass of glyceryl tristearate. It is 891.45. Oops. And I put it in the wrong spot, and that's grams. So this is that's the number of grams that are in 1 mole of that. And then down here we've got moles of glyceryl tristearate, and we're comparing it to moles of sodium stearate. And this is in a 1 to 3 ratio. So 1 of this to 3 of this. And I get these numbers, if you're going between moles and moles, you get the numbers from the balanced equation. If you're going between moles and grams, the moles is 1, and the grams is based on the numbers on the periodic table, the molar mass. And then down here we've got sodium hydroxide. I did not look up the math for that. So we're going to have grams of sodium hydroxide here, and moles. And that's going to be 1. This is the number off the periodic table, so I'm going to leave it for a minute. Down here we're going to say moles of sodium hydroxide, 2 moles of sodium stearate. And the mole ratio here, this one is a 3 to 3 mole ratio. Of course, I could reduce that. 3 to 3 is the same as 1 to 1. All right, I'm going to look up that molar mass, and I'll be right back. Okay, so we've got 100 grams of glyceryl tristearate, and we're going to go to moles of glyceryl tristearate, and then moles of sodium stearate, which I'm going to just abbreviate it like that instead of writing out the whole formula. And so we're going to convert, and we're going to stop at moles. We could go the next step and go to grams of sodium stearate if we wanted to. Either way, as long as we're consistent with our other reactant, we could find the right answer either way. So, got a 1 here. I already looked up the molar mass of glyceryl tristearate. It is 891.45. Oops. And I put it in the wrong spot, and that's grams. So this is that's the number of grams that are in 1 mole of that. And then down here we've got moles of glyceryl tristearate, and we're comparing it to moles of sodium stearate. And this is in a 1 to 3 ratio. So 1 of this to 3 of this. And I get these numbers, if you're going between moles and moles, you get the numbers from the balanced equation. If you're going between moles and grams, the moles is 1, and the grams is based on the numbers on the periodic table, the molar mass. And then down here we've got sodium hydroxide. I did not look up the math for that. So we're going to have grams of sodium hydroxide here, and moles. And that's going to be 1. This is the number off the periodic table, so I'm going to leave it for a minute. Down here we're going to say moles of sodium hydroxide, 2 moles of sodium stearate. And the mole ratio here, this one is a 3:3 mole ratio. Of course, I could reduce that. 3:3 is the same as 1:1. All right, I'm going to look up that molar mass, and I'll be right back. Okay, 39.998 is our molar mass here. And this is the setup that's going to give us the answer to the question, which one is the limiting reactant? Now, to solve this, we're going to multiply everything across the top and divide by everything on the bottom. And same thing over here. So I'm going to do that math real quick, and I'll be right back. Okay, so I've done the math, and I figured out that if I had 100 grams of glyceryl tristearate and enough of the other reactant to make all of this react, I could get 0.3365, probably, well, let's not worry about sig figs on this one, moles of sodium stearate. And if I had 53 grams of sodium hydroxide and enough of the glyceryl tristearate to react all of it, then I could get 1.325 moles of sodium stearate. Again, I could have gone a step further to grams, but I would have found the same answer. And the answer is because this reactant produces the smaller amount of product, this is my limiting reactant in this equation. So the limiting reagent, which one is it? This one. Now, the reason that's important, of course, is because if we actually made our soap with this, even though we have less sodium hydroxide, and it's a 3:1 ratio, because of this huge mass, if we had these two amounts, we would be using up all the glyceryl tristearate and having lots of leftover sodium hydroxide in our soap, which would be really bad for your skin. So we're going to make sure we don't do that when we actually make the soap later today.